All right, so in the lesson today, we're going to be exploring the characteristics of three polynomial functions: linear functions, quadratic functions, and cubic functions. You will note that linear functions were covered in grade 10, Introduction to Applied and Pre-Calculus Math, and quadratic functions were covered last year in grade 11 Applied Math. So really the new function that we'll be learning for grade 12 is those are called cubic functions. However, today in this lesson, we are going to just review some of the basics of polynomial functions. So as we recall, a function, represents a relationship between an independent variable and its dependent variable. And the independent variable typically is designated as y on the vertical axis, and the independent variable is designated x on the horizontal axis, and y is the dependent variable on the vertical axis. So we're working through chapter 6 in your textbook, and there are some review of terms. So we covered off the function. An equation is a representation of a function that has only one distinct answer for the independent variable, and there is an equal sign. So the left-hand side equals the right-hand side. The domain is the complete set of values for the independent variable. Remember that is along the x-axis. Typically in grade 12 applied, we'll be focusing on the interval notation. The range is the complete set of values for the dependent variable, or the y value. And again, we are going to be focusing in on interval notation. However, set notation, set build-in notation, and words you could use as well. Some key points on a graph: where the graph touches the y-axis, that's called the y-intercept. Where it touches the x-axis is called the x-intercept. The end behavior of a graph. The end behavior of the graph is basically the shape of the graph, how it behaves as it approaches infinity. So typically we go from left to right on the x-axis, and we see what the graph does. And remember, there are 4 quadrants. If we go to Desmos here, remember there's 4 quadrants: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And so a graph will always start in one of the quadrants and go to one of the other quadrants. So we will see how that works. Turning points. So as you saw last year in grade 11 applied, a quadratic parabola has one turning point, the vertex. All right, so you'll see what happens with cubic functions. So basically a turning point is any point on the graph where the graph changes from increasing to decreasing, or vice versa. So if it's increasing and then it changes to decreasing, or if it's decreasing, then it changes to increasing. So they could be absolute maximums, or they could be relative maximum and minimum points, as we'll see again when we talk about cubic functions. So just a quick overview here. We have one page. Okay, so we have a graph here, and we would assume there's arrows, okay, because there's no context. So right away, we see that this graph goes up, and then it goes down, and then it goes up again. So right off the bat, we can refer to the turning points, and okay, where the graph changes direction would be defined as a turning point. So this graph would have 2 turning points. Now the end behavior. When we describe the end behavior, we just typically state the quadrant that it starts in and the quadrant that it goes to. So if we look here, the graph clearly starts in quadrant 3 and it goes to quadrant 4 if we go from left to right. So the end behavior would be quadrant 3 to quadrant 4. So quadrant 3 to quadrant 4. Why am I saying 4? Quadrant 1. 3 to 1. If we zoom in closer, we'll look at the we'll be looking at the number of x-intercepts. So it's obvious that there are 3 x-intercepts. It touches the graph 3 points at -2, at 0, and +2. So there's 3 x-intercepts. So again, remember from grade 11, we can state the x-intercepts as coordinate pairs, or we could state them as x equals the value. So we would go x equals, and then we would always start from the left and go to the right. So -2, 0, and 2. So we would go x equals -2, comma, 0, comma, 2. The y-intercept, if we look on the graph, is equal to 0. You can see that on the y-axis, it touches the y-axis at y equaling 0. The range of this, the domain of this, again on the x, if we imagine there's arrowheads here and here, we would notice that it goes all the way from negative infinity to positive infinity. And it never touches negative and positive infinity. So again, we have round brackets for not touching and square brackets for touching. So round bracket, okay, so we'll go round bracket. On Word, you can go insert equation, and you can go negative and then find infinity, comma, and then positive infinity. And we don't typically write positive, we just write infinity. So that would be the domain of this function. And if we notice on the y-axis, if I just view again one page, this starts from negative infinity down here and it goes all the way up to positive infinity. So it actually would be the same. So that's just a quick introduction to how we analyze graphs. And again, if you remember, this is pretty much similar to what we did in grade 11 applied, and certainly what we did in grade 10 intro to applied and pre-cal. So we're not going to do too much of this. We're going to be looking at context, okay, but this is an introduction lesson to the properties of these graphs. So again, we want to be looking for x and y intercepts, x where it touches the x-axis, y where it touches the y-axis. We want to look for number of turning points. We can even identify them. And again, you'll notice when we get to Desmos, all we have to do is click on them and it'll give us the coordinate. The end behavior, okay, always go from left to right. How is the graph moving? What quadrant does it start in? What quadrant does it end in? The domain, the set of the x values, and the range, the set of the y values. Okay, so some important terms then. What is a polynomial function, generally speaking? Well, a polynomial is a function that contains the operations of multiplication and addition with real number coefficients whole number coefficients if it's exactly whole numbers, and two variables, y and x. So linear would be y equals x. Quadratic would be y equals x squared for quadratic. And if we looked at cubic, cubic would be y equals x to the power of 3. Okay. Of course, these functions go beyond 3. You can have a quartic function, which is to the power of 4, to the power of 5, to the power of 6. So all kinds of different ones. But for grade 12 applied, we will be focusing on y equals x squared, and y equals x cubed. We won't do too much with linear, but again, for today's lesson, it being an introduction, we will consider the properties. So we'll begin. So if we just do a general function, y equals x, okay, snip this, there we go, okay. So all I'm gonna do is take a snip of the graph as an example, and you can see the general properties of a linear function. Make that a lot smaller. So as you can see, the red line is y equals x. So the domain, as we can see, it goes left to right. Imagine it's arrowheads, so negative to positive infinity, as well as the range. And again, this is without context. Very important to note. So this is review. So there is no context here. No context to the functions. When we get into context, we cannot simply blanket state that the domain and range will always be negative to positive infinity. Okay, we usually will be hanging out in quadrant 1, just as we did in grade 11. But for the purposes of today, we'll just consider no context. So the domain would be negative to positive infinity, and the range, the y value, going negative to positive infinity. How many x-intercepts would there ever be? Well, in this case, there's only one. Very important to note that the number of x-intercepts, number equals the degree of the function. Okay, so, and I should say the maximum number of x-intercepts would be the degree of the function. So at any time, you can only ever have, for a linear function, one x-intercept. It being a function, functions only ever have one. Okay, so no matter what the degree is, there only will ever be one. It's underlining. Okay, what's going on here? This is annoying. That's okay. Let's go control U, control U. Okay, no, control U. Get out of there. Okay, so a quadratic would only ever have one x-intercept as well. I mean, one y-intercept. Okay, the end behavior, well, in this case, the end behavior goes from quadrant, if we go back to the Desmos, if it's positive, it goes from quadrant 3 to 1, but if we put a negative in front, notice it goes from 2 to 4. Okay, but our example was positive, so of course it goes from 3 to 1. And again, when we state the end behavior, it's always based on the graph that we observe. So the end behavior would be Q3 to Q1. Number of turning points, a line, just the linear function just goes straight up or it goes straight down. There are no turning points, so there would be none. Okay, so we'll go look at a quadratic. So we'll make a quadratic. We'll go, in this case, we'll go y equals x squared, and we'll just bring it down, the vertex minus 4. Okay. All right, so here, again, as a review, remember for quadratics, when that value in front of the x squared is positive, the parabola opens up. If it was negative, it opens down. So for our example, we'll make it positive, and we'll snip that. Okay, copy that and paste it into our Desmos. Okay, so we see it's a lot different than the parabola is much different than a line for linear. It is symmetrical. Remember, it has a vertex in the center. That vertex is the turning point, ironically, interesting. And of course, we have an axis of symmetry that's always vertical. So the domain, as we can see here, if there's arrowheads, negative to positive infinity, again, without context. But range is different. Remember, because this is a minimum, the range would have a smallest value, which it touches, and then it would go up to the maximum value. So if we're going to do our set notation, it would touch the smallest value, the range, so we put a square bracket, and that value is -4. And it would go all the way up to infinity, and we would put a round bracket after that. Okay, so how many x-intercepts? Well, this graph clearly has 2. Again, it's degree 2, so there should be 2. But of course, if we go back to Desmos, if we took away the -4, then you would see that this would just have 1. So again, back to the notes, the maximum number of x-intercepts is the degree of the function. So it could have 2, or it could have 1. It could also have none. Y-intercept, well, there's only one y-intercept. It touches at -4. The end behavior of this graph starts at quadrant 2, and it goes to quadrant 1. Quadrant 2, quadrant 1. The number of turning points, well, there is 1, the vertex, 1 turning point. So that's just a brief overview of linear and quadratics that we did in grade 10 and that we did in grade 11. So now let's take a look at what a cubic function is. So a cubic function is defined as a function, oops, what am I going on? It is defined as a polynomial function of the 3rd degree. Example, y equals 2x cubed minus 3x squared plus x minus 7, or sorry, minus 6. So that would be a cubic function because the degree 3 is the largest. Okay, well, I think we're going to look at this and see what graph this would look like in Desmos. So I'm just going to copy that. And we will paste it. And we'll have to go in here. Okay, so what you want to do to the power of anything more than 2, you go a to the b, so you go 3, and then minus 3x squared. Whoops. Okay, there we go. Okay, so, no, zoom in. All right, so we can see that this graph comes from negative, goes up a little bit, and then down, and then back up. And it only has one x-intercept. So we'll snip that. And we'll copy that into our document. So just for the notes, make sure you are typing in that equation. Okay. So again, a cubic function, the domain without context, again, this would be going all the way to the left and then going all the way to the right. So it would be negative to positive infinity without context. And the range would be the same, going from negative infinity all the way up to positive infinity. In this example, there is only one x-intercept. There's only one. In fact, the x-intercept in this case would be 2, x equals 2. There is one y-intercept, -6. So 0, -6 is the y-intercept. Interesting, remember it's equal to the constant term at the end. And x equals 2 is the x-intercept. Okay. So there's one y-intercept. The end behavior of this graph, it goes from quadrant 3 to quadrant 1. And there are 2 turning points. So if we click on them, again, I told you Desmos would identify them. If I click off that, so I'll zoom in here so we can see it a bit better. So there we go. So here we have our first turning point, 0.211 comma negative 5.904. That's kind of like where it gets the largest. So we would call this a relative max or relative maximum. And then it kind of dips down to a relative minimum at 0.789 comma negative 6.096, and then it swings back up. So it turns direction twice, so 2 turning points. When we talk about the relative maximum or minimum values, we're always concerned about the y value. So the relative maximum here would be negative 5.9, and the relative minimum would be negative 6.1. So there's 2 turning points. Okay, so the standard form of a polynomial function. The standard form of a function, of a polynomial function, okay, looks like this. So it has leading coefficients and a constant term. So for example, if we're talking about linear and then quadratic and then cubic. The linear would be y equals ax plus b, where a cannot equal 0 and b would be the constant term. Quadratic, you would have y equals ax squared plus bx plus c. Of course, where a cannot be equal to 0 because then it would be a linear function. And cubic, the standard form would be y equals ax cubed plus bx squared plus cx plus d, where a cannot equal 0. Again, a, b, c, and d are just coefficient, or sorry, a, b, and c are coefficients, and d is the constant term. So remember that coefficients are always in front of the variable. Okay, so in linear, the last term is always, in linear, quadratic, cubic, any polynomial function, the last term is typically the constant. So obviously you can explore that if you change any of these coefficient values, it's going to change the shape of the graph, and you would be able to explore that. So what I'm going to leave you guys to do, and I'll show you what to do, but I'm going to leave you to basically plug these equations into Desmos and then copy paste the graph so you can kind of see what they look like. So I'll do one of each and then you can see what they look like. Okay, so if we want y, we'll do y equals 2x plus 1. So we would go to Desmos. I'm going to reset it. And you would type in y equals 2x plus 1. Okay, we're going to click on some important points here, the x-intercept and the y-intercept. Remember, if you click on the important points and you have your snip tool open, okay, you can snip the graph and it keeps the important points. Versus if you try to export the graph, the points go away. So always use your snipping tool. If you have a Mac computer, then figure out how to use the Mac computer. I believe it's like Command F3 or something. Google it. But if you have a PC, then open up Windows snipping tool. So when you snip, it catches the picture, right-click, copy, and then you would just Control V into Word and just make it small enough that it fits on the page. Okay, so again, the purpose of this practice is just to sketch and analyze. So when we say analyze, we can talk about the end behavior. So this would go quadrant 3 to quadrant 1. X-intercept would be x equals negative 0.5, which is right there. Y-intercept would be y equals 1. Okay, so we'll state the end behavior, the x-intercept, the y-intercept. It has turning points, none for linear. And what else should we analyze? The domain and the range. So D for the domain, R for the range. So the domain here, no context, and negative to positive infinity. So I'm going to go back and copy that. And the range would be the same. Okay, so then you can try that for the second example for the linear. Okay, so copy paste the graph in, end behavior, x and y intercepts, the number of turning points, and then the domain and range. Okay, so we'll try one for the quadratic. Actually, I'll leave both of the quadratics for you because that's a review. All right. As you insert the graph, it'll extend the Word document, so you shouldn't worry about that, and then you can print it off after you're done. I would just work on this as a Word document on your computer. We will do one of the cubics though. Okay, so I will just put this on a new page. So y equals x cubed plus 3x plus x plus 3. So everything's positive. Okay. I'm going to reset the graph. So y equals, I already forgot it, x cubed plus 3x squared. So x cubed plus 3x squared plus x plus 3. So plus x plus 3. Okay, so there's our graph. We want to click on all the important points. So in a cubic, it'd be any of the x-intercepts, the y-intercepts, and then the relative minimum and maximum. So we have an x-intercept, a relative max, a relative min, and a y-intercept. And they're really close together. So I'm going to just, if I zoom in, there we go. So x-intercept, relative max, relative min, and y-intercept. So we're going to capture all of that with our snip. So new snip. And then we will capture all of that like that and try to get the x and the y axis here. As you can see, x and y. Copy. And we will paste that into Word. Again, just shrink it so it doesn't take up the whole page. It doesn't need to, as long as you can see the numbers. Okay, good. And we're going to do all of this stuff up here. So I'll just copy paste and we will redo that. Okay. It's in red. Let's do this in red so it emphasizes it. Okay. So the end behavior. Well, the end behavior of the graph, it does start again in quadrant 3 and it goes to quadrant 1. So that would be the end behavior of the graph. So quadrant 3 to quadrant 1. The x-intercepts, there's only one. So that would be x equals -3. The y-intercept would be y equals 3. Again, it's the y value. It's the y value of the coordinate, and the x-intercept is the x value of the coordinate for the x, or for the root. Turning points, well, here we can see that it turns once and then it turns twice. So turning points, there's 2 of them. We may as well state their coordinates. So -1.82. We're going to 2 decimal places. 2, and they are -1.82, 5.09, And the second turning point would be negative 0.18, negative 0.18, comma, and the y value would be 2.91. Again, the first point is a relative maximum. And the second one would be the relative minimum. The domain in this case is like the first one. It goes from negative to positive infinity, and the range goes from negative to positive infinity. So there's no context, so that would be that. So I'll leave you with the second linear, both quadratics, and the second cubic. So if you could do what I did here, plug it into Desmos, click on all the important points, snip it, copy paste, and then end behavior, x-intercepts, y-intercepts, turning points, what they are, and domain and range, and then answer the questions 1, 2, and then there is another practice for you here. So you can try that on your own, and then you can work through the homework. And we will be covering this stuff on our Zoom meeting on Friday. So if you have any questions, don't hesitate to email me, but that pretty much covers our lesson for today, introducing polynomial functions.